Now we're going to look at convex mirrors. So convex mirrors are curved in the opposite way. So the focal point is behind the mirror and the center of curvature is behind the mirror as well. So both the focal point and the center of curvature in virtual space, negative, but we put the equivalent F and the focal point and C on this side, the same distance, right? So if the focal point's here, this is where F prime would be. If the center is here, this is where C prime would be, or C apostrophe. So again, we're going to look at what happens when I have the parallel light coming in and stuff. So if I have a beam of light coming in, then what happens is that it gets reflected out. So we call these diverging mirrors. The other ones we call converging because the light comes through the focal point. Here it seems to scatter and the parallel light comes out and it reflects as if it's coming from the focal point. Right? So if my parallel light comes in here, it will go out here. And we use this as heat diffusers or as light diffusers in photo shoots. We use this to soften the light. So if you often see those people using those flexible, reflective foam surfaces behind a mirror, or if they have the cones, those are often angled, they're convex, so that whatever light I'm shining on gets reflected away. And so I soften the light behind the person. And then if I have light coming in from an angle, then it comes back parallel to the viewers. And this is really important for traffic mirrors. So these are positioned in areas where it's hard to see around a corner. People sometimes put them at the end of their driveways so that they can basically see, if I'm here, I can see a car coming from behind a corner, right? So it allows the viewer to see objects that normally wouldn't be able to be seen with a plane mirror, and is very important when it comes to just traffic safety. So here's a sample diagram. We use the same idea where I have my angle parallel, and then it's going to go reflecting back as if it's from my image, and then one that goes straight to the center. So remember that the focal point and the center are over here. So when my light comes here and it bounces back, I'm going to be coming back through the focal point here and then going through as if I'm going through the mirror. And where they appear to intersect is where my image is going to be found. So in this case, my object is between the center and focal point, right, as if it were on this side. And my image is behind and it's closer to the mirror. It's upright, it's smaller, and it's virtual. So that's a sample ray diagram. So we're just going to go through those same 5 points where I am in relation to my center and focal point and just draw those same rays again. So this is if my object is farther away from the center or the equivalent center. So I draw my first ray to the mirror and then to the focal point on the other side. And you can dot this line if you wanted to show that it's in virtual space, or you can keep it solid, it doesn't really matter. And then from the center, from the top to the center on the other side. And where they intersect, right here, is where the head of my arrow is, and my image is going to be there. So if I want to do lost, my image is closer, it's upright, it's smaller, and it's virtual. What if I march my object to the center? I do the same thing. And notice that I'm using the same colors each time for my 2 rays. This is, again, if you're into color coding like I am, then this can be one of those things that really helps visualize what we're supposed to do. Again, from the top of my object to the center. And again, they're both on the other side of the mirror. And my object is, it's getting slightly bigger. So it's still closer, upright, smaller, and virtual. But you can see that it's getting slightly bigger. If I then take, now I'm between the center and the focal point. And I've kept my object the same size and my focal point is the same so that you can start to see the So still closer, upright, smaller, virtual. I'm now at the focal point. The focal point, remember with the concave mirror, was where my object disappeared. So let's see what happens with this. Take it to my mirror, to the focal point. To my center. And nope, my lines are going to be intersecting. And so I still have an image. So unlike a concave mirror, I don't have an instance in which my image disappears. I'm closer, upright, smaller, virtual. But it's getting a little bit larger, right? Not getting that much larger, not getting that much closer because I'm already close to my object. Let's say that I'm between the lens and the focal point. So now I'm in front of the focal point, really close to the mirror. My same two lines. Wow, no, always, no matter where my object is, right? Whether I am far away from the center, getting closer, bringing my object even closer, here, right now my object is right up against the mirror, and I still have the same. My object is closer to the mirror, it's upright, it's smaller, and it's virtual. So what do we use these for? We use these for our side view mirrors. If you've ever noticed on your side view mirror, there's oftentimes a little disclaimer that says either objects in the mirror are closer, objects in the mirror are smaller than they appear, or larger than they appear, sorry. So basically what it's saying is that when I see the image, I have to realize that this image is actually smaller than it would appear. And here's the thing, our brain, even though that image appears closer to our mirror, our brain knows what the size of objects should be. And it thinks to itself, well, if it's smaller, it must be farther away. So another thing that it might say is it might say objects in the mirror are closer than they appear. Here's the thing, if I see a truck in my side view mirror and it appears smaller, my brain's not going to think, oh, the truck must have shrunk. My brain's going to just, in that quick glance of looking at the truck in the mirror, think that it's farther away because when something's farther away, it looks smaller. And I have to be reminded of that. The nice thing, the reason why we use convex mirrors is that one, I could see farther around, like that traffic thing, but my image never disappears because that would be bad. And it's never upside down because that would be slightly disorienting. You never want a situation in which I look outside and I'm momentarily confused. So if I look outside and I see an upside down truck coming toward me, I'd be like, what? And I have to keep reminding myself. So we don't want things like that to distract us even momentarily when we're driving. So we use these convex mirrors, one, so that we can see farther around the side of our car, but also so that our image is always upright and coming toward us. But because all of those images will always be smaller, we have to be reminded that that image is actually closer. So if I see it on a traffic mirror and the car appears smaller, I may think that I have more time to make that turn into traffic because that car appears smaller. It must be farther away. When in reality, it's actually closer. It just looks smaller because of the mirror. So this is one of the examples of how we use convex mirrors and how they obey the laws of reflection.